Good afternoon, agents. This is Dr. John Galbraith. Today I'd like to present an introductory level webinar, January 12, 2015. Today's webinar will be called Common Soil Types in Different Regions of Virginia. First, I'd like to introduce myself. I am a soil information specialist in Blacksburg with Virginia Tech, and I've been a soil scientist since 1983. I've had the opportunity to work in several states surveying soils with the Natural Resources Conservation Service. And then I've also been a teacher at Cornell, University of Florida, and Virginia Tech. I'm very pleased to be here in Virginia, and today I think I can point out a few things about the soils and the different regions of Virginia that may be of interest to you. I'd like to remind you that you do not need to use your video, but that I will ask you to mute your microphones, use the chat service to contact me and ask questions, and also I'd like to alert you that this video will be recorded, and that the recording will be posted on the Virginia Cooperative Extension webpage. Well, let's get started talking about the soil types in different regions. Let's start by talking about the different regions. Another name for that is provinces. And we can start from west to east with the Appalachian Plateau, go to the Ridge and Valley, the Blue Ridge, the Piedmont, and the Coastal Plain. Well, that sounds like a pretty simple journey or explanation, but it's not quite that easy. And to understand the state and the soils, then we really need to understand what kind of rocks and parent materials there are underneath. So let's start with this graphic. And we can separate the rocks and the soils into two or three main types. So in the Appalachian Plateau, in the Ridge and Valley, we have primarily sedimentary rocks. We also have sedimentary rocks in these little orange diamond-shaped areas called Triassic basins. On the lower drawing, that is shown in green. That is sedimentary rock. The crystalline rock, which would be found in the Blue Ridge and in the Piedmont region, and deep underneath the Ridge and Valley and Appalachian Plateau, these crystalline rocks are igneous and metamorphic rock. The bottom figure shows this very, very well. It shows the separation of the purple sedimentary rock, and then the green area has sedimentary rock, and then the crystalline rock, which is igneous and metamorphic, is in orange. On top of the Piedmont rock and on top of some of the basins, these are called Triassic basins because they were geologic low areas that filled with sediment. That sediment turned to rock long, long ago. But a much younger feature is this wedge of sediment called the coastal plain sediments. They're called sediments because they've never been deeply buried or turned into rock. That term is called lithified, turned into rock. And this material is cemented in places by secondary minerals, but for the most part it's sand, silt, and clay with some gravel in places. All right, so understanding that we have uncemented material in the coastal plain, for the most part, loose sediment, that we have igneous and metamorphic rock in the Piedmont, and that we have sedimentary rock in the Triassic basins, the Ridge and Valley, and the Appalachian Plateau, helps us to understand then what kind of soils we can expect. Here's a actual elevation map of Virginia, and it does show the boundary between the Appalachian Plateau and the Ridge and Valley, and that boundary can be identified through the folding of the rock layers. And the most resistant rock layers form the tops of the ridges, and the less resistant rock form the valleys. And then the Blue Ridge area also has some folding in it, but not to the extent that the Ridge and Valley does. So we have Appalachian Plateau, Ridge and Valley, Blue Ridge Province, and then the Piedmont. Let's start with the Appalachian Plateau. We have long, steep slopes, very, very steep and very, very continuous here. We can see this. That indicates that this river has downcut very rapidly and so has this side stream. In fact, it's probably not much more than a small tributary, but it has done tremendous erosion, and a lot of that erosion probably took place during the glacial periods. It's probably much more stable now than it has been in a very, very long time geologically. But we get very narrow valleys, not much of a floodplain or terrace system at all in the bottom. These rivers, that indicates that the rivers are downcutting very rapidly and that they're not meandering from side to side, which you would find in more level areas of the state. Another interesting thing, the reason it's called a plateau, is you can see here that most of the mountaintop elevations line up. Now, it's not a perfectly level area, but for the most part, the same bedrock types, where they occur, they will line up and correspond with each other. Well, here's a view of a road cut that shows alternating layers of sandstone, that would be the gray rock, and then shales, that would be the maroon colored rock and the very dark colored rock. Every once in a while you get a layer or a seam of coal in that region, and that would be the very dark colored areas. And for the most part, this bedrock is very acid. At the top you can see more massive sandstone, and that would be true. Next time you drive through West Virginia or Western Virginia, take a look at the road cuts, and you'll note that at the top of the mountains you find sandstone, and then you find the shales underneath the sandstones. The sandstone is more resistant to erosion, and that's why it protects the landform from being eroded. Well, let's take a look at a common soil. This would be an example of the Gilpin series. Does not have much water holding capacity. It's not very deep. It's what's called moderately deep, meaning it's between 50 and 100 centimeters or 20 to 40 inches of soil before you hit bedrock. Now, the bedrock seems to be highly fractured here, and so roots are able to go down in these cracks, but roots are not able to penetrate the sandstone fragments. So therefore, most of the vegetation roots run parallel to the bedrock surface. These soils are continuously being, assaulted by gravity. The soils get wet, and they're on steep side slopes. They tend to move down the slopes, and that we'll explain that in just a minute. But in this particular picture, you can see that the rock types in the soil match up pretty well in shape and size with the rocks underneath. The difference being that the rocks near the top have weathered into soil material, and the rocks underneath are not yet exposed enough to have become weathered. So we would think that this soil material above these rocks probably formed from a very similar type of rock, and we would call this parent material residuum, meaning it resides where it was born. It lives where it was born. It's residual. Here's a picture of another soil that has fewer rock fragments in it, but you can tell by the vegetation, this is pitch pine and Virginia pine, pretty poor quality, low yielding types. And the soil is so acid, there's just virtually no fertility in these soils, and we have a limited rooting zone. And so again, this soil is 20 to 40 inches deep over bedrock, the DeKalb series. This soil does not have an accumulation of clay in it. The Gilpin series does have an accumulation of clay, and so even though both soils are moderately deep, the Gilpin series would have higher water holding capacity than the DeKalb would. Well, here's two other very common soils. The two previous soils I talked about formed over sandstone. These two soils form over shale. And we have the Weichert series, and you can tell right here at the top of the W, that soil is less than 20 inches deep before you hit the shale bedrock, as shown in the gray here. The Birch series on the right-hand side is the deeper soil. That is, again, moderately deep. It's 20 to 40 inches. The difference between the Birch soil and the two previous soils is that it formed over shale instead of sandstone. The Weichert soil is extensive, as is the Birch, and there are places in Virginia where you get barrens or areas where there's shale exposed at the surface, and those very shallow areas are associated with the Weichert series. Again, very, very acid material. Now, as a surprise, found in foot slope and cove areas, we get what's called colluvium. And colluvium is when gravity forces soil that becomes oversaturated and it forces it down the hill. And so the soil would flow wherever the water would flow. And in these water collecting landscapes is where you have sediment collection. And again, this is not sediment that's carried in a channel. This material moved under the force of gravity. You can see a mixture of rock types and sizes in the soil. Some of these are sub-rounded, and that means they've probably been transported great distances. The rocks in the Gilpin soil were quite sharp on the edges, indicating they had not been transported very far at all. This Jefferson soil is a very, very good soil, and it has a mixed fertility level. It's not as acid as the Birch, the Gilpin, and the DeKalb. It has better fertility because it has a mixture of rock types in it, not just acid rocks. We also get soils on river terraces. There are not very many river terraces, but some of the valleys do widen out. And these are ancient river terraces, meaning they're not associated with the current stream, but were probably deposited by the ancestor to the current stream. So we get these broad, nearly level areas adjacent to stream floodplains, and these are typically the Monongahela soil, which is the state soil of West Virginia. Our state soil is the Pamunkey, and we'll discuss that later on when we discuss the coastal plain. But in this soil, we get a restrictive layer at about 36 inches, and that restrictive layer is called a fragipan. And this particular soil is still one of the most productive soils in the region because of its level nature and because it does have 36 inches of good soil. So it essentially has as much good soil as the Gilpin, the DeKalb, and the Birch over the top of this fragipan. It has the same amount of good soil, but it has fewer rock fragments and it's more level, so more of the water infiltrates. It's also a river deposit, and so it tended to have a high mixture, the greatest mixing of rock parent materials, and therefore it has the highest natural fertility in the upper part. All right, let's move on now to the Ridge and Valley province, and again, these are the same bedrock types, only they've been folded and faulted and greatly eroded. And we can see in this picture that down in the valley bottoms, we have our limestone soils. And each time we cross a ridge, the soil will instead of being a limestone soil, the soil will become a shale parent material. And then we go down the ridge and up on the next ridge. In the next valley would be limestone. The next ridge would be shale. And then at the top would be sandstone. And the sandstone is very, very resistant and highly tilted. So some places the sandstone sticks right out of the ground, almost straight up into the air. And here's a picture that shows that orientation of sandstone and shale. In this particular case, most of this material is shale, but it does show you one of the lower ridges and why you have shale there rather than limestone or sandstone. So this is a lower ridge, not at the tops of the mountains. Very interesting bedrock. All right, again showing the limestone valleys with shale on the lower ridges and sandstone at the top of the ridges. Colluvium would collect at these foot slope positions, and that is where the Jefferson soil would be found. Other soils formed over limestone are found in the valley. And here's what the limestone looks like, and the shallows of the limestone soils is called carbo. And this soil is less than 20 inches before you hit the hard limestone. Interesting to see the tilt on the limestone, and also to see that there are springs that do pop out in places. Here's a spring box, and you can see some water coming out of the ground on the right-hand side. Unfortunately, this particular field has been overgrazed, and that's why we see erosion. And once the subsoil is exposed, it's very, very difficult to revegetate these areas. But this is called the carbo soil. Soils that are just slightly deeper than this are called Caneyville. And if you get slightly deeper than that, then you get Gross Close and Poplamento soils. Well, this is the Caneyville soil, and it's found in the valley bottoms. And you can see it's deeper to the hard limestone. It does have some fragments of limestone scattered throughout, but for the most part, it's a good silt loam surface with a clay loam to clay subsoil. And the fertility is good because it is forming from limestone. And limestone and dolomite rocks are very, very fertile, as completely opposite of the shale and sandstone that's found in the same region. So that's why the valleys are farmed, because they have natural fertility and higher water holding capacity, and they're less steep. The side slopes and the tops of the ridges are not farmed because they are very infertile, have a low water holding capacity, and really tremendous runoff. It would be very dangerous to leave that surface plowed. Well, here's what the deepest soils, the Gross Close and Frederick, is a soil that I had not mentioned. The Frederick is the reddest of the limestone soils. The Gross Close is more of an orange color. But you can see by the size of the shovel here, you can see that this soil is very deeply weathered and that the limestone is completely gone. It's been dissolved. So these are moderately fertile, and the clays have quite a bit of ability to hold on to nutrients if you add them. Well, you can see that where these soils occur on slopes that are not excessively steep, they are farmed, and you can still raise corn and small grains in these areas quite readily. Again, in these ridge and valley, we have the Berks and the Weikert series discussed earlier. The Berks, again, the deeper soil. The Weikert is the shallower soil over shale. The difference being that in the Appalachian Plateau, when we discussed these two soils, we showed that the bedrock was horizontally bedded. Here, the bedrock is nearly vertically bedded. Well, that actually means that this soil, it's easier for water to get down through these rocks and easier for roots to tap into the top of these rocks. Unfortunately, the rock itself is very infertile, And that's why, again, the vegetation is not very good on these two soils. If we go to the tops of the ridges, we get the hard white sandstone. That's called the Tuscarora sandstone. Often you'll find little pebbles inside the sandstone that are quartzite, and that's an interesting story. But here you see the picture of the Tuscarora sandstone, and it often is exposed because it's so hard to weather that once the soil gets eroded off the top of it, it just it's so resistant to weathering that very little new soil forms from it. Some soil does form in the cracks, but very little forms on the rock itself. Well, let's talk about the Blue Ridge province now. And here you see Christmas tree farms, and you might also find some orchards or vineyards in this region. The rest is pasture or forest. The soils have higher fertility than, these are the crystalline rocks now, crystalline, igneous, and metamorphic rock. We call them crystalline rock because you can actually see crystals of different minerals. And in this region, these crystalline rocks contain a higher fertility because they have primary minerals. And so they weather into soils that have a little bit higher fertility than the soils on the ridges of the ridge and valley and the soils of the Appalachian Plateau. The limestone soils in the valleys of the ridge and valley are more fertile than the soils in the Blue Ridge, however, because they did form from limestone. These are the steep slopes. Most of this would be in the Blue Ridge Parkway, Jefferson, Washington, Jefferson National Forest. You can see the metamorphic rock here. This is gneiss, G-N-E-I-S-S. It's a type of very, very resistant metamorphic rock with lots of quartz in it. And you can see the Blue Ridge landscape here, where we have mainly pasture land. These would have been active fields 100 years ago, but most of these fields have a low reserve fertility, and therefore without fertilizing, they tend to be depleted of nutrients very fast. And so a lot of those were replaced from farmland into pasture. Another reason they were done that way because was to stop the erosion. But there are quite a few farmsteads in the region, and of course most of it is very beautiful, and so a lot of people live there for the scenery. Now this is granite that's at the top of the Blue Ridge Parkway, and the trees are quite stunted because this granite is very massive and very resistant to weathering, just like the Tuscarora sandstone. It is higher fertility than the sandstone, and it does weather more rapidly than the sandstone. But these soils are typically in parks, and there's not much you can do with them other than wildlife land or recreation land. Moving down the side slopes, then we get to the Glenelg soil series. This is a soil that is fairly red. It's usually a deep soil and has a moderately high water holding capacity. It's very acid and low fertility. That's its drawbacks. But if it is amended with lime and fertilizers, then it has a pretty good capability of being used for numerous types of crops. Natural fertility would be low, but the ability to hold on to nutrients would be, well, it would be better than the soil that formed over the sandstone, but not as good as the limestone soil. This soil has accumulation of clay in the subsoil, and almost all of the soils in the Blue Ridge have that. They have bright red subsoils in places, and they resemble the soils of the Piedmont. This is soil where gravity has transported the sediment and the rocks down the slope, and you see big boulders of granite that have come from nearby mountainsides. They've traveled a long distance, and that's why they're so rounded. However, they still contain primary minerals, and when they weather, they produce a red-colored subsoil that's it has a fairly good water holding capacity, except for where the rock fragments are. This is the Piedmont region. You can see in the background that the soil shows some of the orange subsoil exposed at the surface, and then other areas that are more beige colored where the topsoil still remains. The Piedmont was subject to severe erosion during the 1920s when the boll weevil attacked, and so a lot of the soils have been badly eroded, and now they are retired to pasture land. So former cropland is now pasture land in large areas of the Piedmont. Well, this is the Piedmont metamorphic rock, and these layers used to be level or flat bedded, and then by being under intense heat and pressure, they actually melted and recrystallized into new layers, and you can see what kind of pressure they were under by the shape of the layering. So the white areas are quartz, and this soil again is gneiss bedrock, Gneiss, a metamorphic rock. Well, most of the Piedmont now is foraged with some woodlands. As we get to Appomattox and go further east, you see more and more of the pine plantations, but on the western side of the Piedmont, it's mainly pasture land. Very, very beautiful land, but highly erosive. And so most of this area, even though a lot of this was farmland at one point in history, most of it has been put into pasture land and is grazed now. As you get to the eastern side of the Piedmont on the more level soils, they still grow tobacco, corn, soybeans, small grains. You can see how orange this soil is to the surface, and that indicates that it's been highly eroded at some point. And this is the soil that you would find underneath in an uneroded condition, and this is called the Cecil series. And it's very extensive, bright red. The soil is dominated by low activity clay, meaning it's very infertile clay. So even though the percent clay may be 60-70% in these subsoils, the amount of fertility is usually quite low. Now, the Cecil is the most common series found throughout the Piedmont, but the Appling series is very similar. However, the Appling is a more orange color, and it probably is transported material, whereas the Cecil soil fairly well matches up with the bedrock underneath it. So most of the Cecil would have formed from the rock underneath, and you can tell that because the rock underneath has mica, and the Cecil series has mica in the lower subsoil. That mica is gone from the upper subsoil and the topsoil because it's weathered away. These soils are very acid, but they can be fertilized and limed and then used for production. This is a gneiss soil. It has much more silt and less clay than the Cecil and the Appling. This is the Packlet soil, and the difference between it and the Cecil is that it has saprolite that comes in closer to the surface, as shallow as 30 inches here. Now this is the saprolite. You can still see the original layering from the metamorphic rock here, even though most of this has turned into soft material that you can put a knife in it and cut it, or cut it with a shovel very easily. So this is bedrock that is completely weathered, and it's called saprolite. Down in the saprolite are clay flows, and the clay flows, that's where the roots will follow the soil down between the pieces of saprolite. The soil above the saprolite is very similar to that in the Cecil. It's just not as deep. This is the Tatum soil. This is a moderately deep version of the gneiss soil. So Pacolet is a moderately deep version of Cecil, and Tatum is a moderately deep version of Nason. Well, this is one of those Triassic basins, and this mudstone is some of the sedimentary rock that's found in the basins. This looks like the type of mudstone that you would find up around the Culpeper Basin. Now, it's called mudstone. It is sedimentary, but it's very high in silt and clay, and it cracks apart very readily, but it's not thinly bedded like shale would be. It has been turned into rock by heat and pressure, but not intense heat and pressure. And so it weathers fairly easily into clayey materials. This is a picture of the soil that formed from it. And these soils have a moderate fertility, not as high as limestone, but probably as fertile or a little more fertile than the soils of the Piedmont. Again, probably one of the limitations, many of the soils over the Triassic basins are moderately deep, and some of them have a very high clay content in the subsoil. It depends on whether the soil formed from a mudstone or whether it formed from an igneous rock that was found in the basin. The igneous rocks tend to form shrink swell clays, and other soils with high clay content, it's quite impervious to water. Well, this is the coastal plain, and we're all familiar with this region of the state, and most of our population either lives in the coastal plain or right on the margins of the coastal plain. And this particular soil is a good sandy, white-colored quartz sand, and it's growing peanuts. In the background is some corn, and then we have lots of loblolly plantation. Well, here we can see the coastal plain as seen from an actual elevation map. And deeply incised are these estuaries. These are old river basins that made very wide rivers during the Ice Age, because the water in the Atlantic was 300 feet lower than it is now. And as the water has been coming up now, it has flooded these river valleys. So this would be the James River, the York, the Rappahannock, and the Potomac. Richmond would be found here on the fall line, Richmond and Petersburg, Washington, D.C., and Alexandria. To the west of that are the Triassic basins, and that's where that mudstone would be found, or igneous rock. Well, this is what the sediments look like in the coastal plain. Very seldom do you actually get to see the sediments, but this particular cut we were able to get a picture of. There is soil on the top, but you can see the layering, thin layering. So each flood event from rivers deposited sediment, and this area has never been deeply buried or compressed or heated, and therefore it's not bedrock, it's sediment. You can see some areas that used to be organic material, and if this area were to ever turn into hard rock, this would turn into coal right here, this seam in the middle. This would turn into sandstone, and some of the clayier material would turn into shale. Some of these areas have quite a bit of gravel in them too. Again, this is where the rivers flowing out of the Piedmont and the Blue Ridge deposited sand, silt, and clays. And then the ocean also deposited material. Well, this is a well-drained coastal plain soil, and it has a nice accumulation of clay in the upper subsoil. But these soils are typically pretty well leached, and so their fertility is not extremely high, but it is probably as high as most of the Piedmont soils, because it does contain some mixture of sediments that would have drained the limestone valleys. Most of these soils have a very sandy cap with a moderately clayey to highly clayey subsoil. This is the Slagle series. This picture is not very good quality, but I think you can see a color pattern in the lower subsoil, and that indicates restricted drainage. So the Slagle series is one that is a deep soil, but it does have restricted drainage, and therefore it's moderately well drained. It has some wetness features in the lower part. Well, we get to, here's another soil where you can see the wetness features. The gray indicates reduction of iron because of extended saturation in this subsoil. And then there's accumulation of oxidized iron in other parts of the same horizon. So essentially, the iron moves out of the gray areas and moves into the red areas and accumulates. We'll be discussing that more in a later lecture. Here's a soil that is even wetter, and you can see that majority of the horizon is turned gray due to reduction of iron, but then you can see areas where that iron has moved and precipitated into a concentrated area. You can also see some black areas, some zones of black, and this is not charcoal, this is actually manganese oxides, and the manganese combines with iron and precipitates. The manganese is also reduced in these gray areas, and it migrates to the black areas with the groundwater. This is the Roanoke soil, and this soil is quite clayey, very near the surface. It has a fairly dark or dark gray surface, and then the entire subsoil is gray. These soils have a water table, as shown at the bottom, that rises and falls during the year, and during the year it may come all the way to the soil surface, but then it drops during the middle of the summer when the evapotranspiration is high. This is a poorly drained soil, and that means that we have gray colors directly underneath the topsoil. And here's another poorly drained soil, and during the winter months these areas typically pond water. Here you can see how dark the surface is and thick, and that's because we have the organic matter in these soils stays so wet that it really can't decompose very well. And so the organic matter builds up in these soils over time. This is the new flat soil that's found on dunes near the beach, and these dunes are extremely important features and need to be protected. You can see what happens when they become unvegetated. Well, they begin to blow and the soil moves, and so we really do need to protect these by keeping them vegetated. Well, that's the end of our talk today. I hope you've enjoyed it. We've covered the soils all the way from the Appalachian Plateau through the Ridge and Valley to the Blue Ridge, then to the Piedmont, the Triassic basins within the Piedmont, and then the coastal plain. So our next webinar will be an intermediate level webinar, and we look forward to your participation. I hope you enjoyed it, and I hope you have a great day.